Okay, so previous class we've been talking about position vector directed force, right? And the reason why we are talking about this is because for previous problems that we've been talking about. So we only so for the direction information of the force, it has already been given, right? But in reality, so those kind of information is actually is inherently in the geometry information of a structure system. Okay, so how can we relate the geometric information with the direction of forces? So that is actually the reason why we are talking about position y vector and directed force here. So first we introduced that given that there's a point A and B, okay? Given that there's a point A and B, okay? So we defined position vector is actually a vector pointing from one point to another. So for example, the position vector from A to B is defined as is exactly a vector from A to B. And its Cartesian format is pretty straightforward given the coordinates, right? It is so the coefficients of the components are actually using the coordinates of endpoints minus the coordinate start point. So, and we went through an example here. Okay. So after the example, we also introduced if we have a force along the line from a point to another. In other words, we can see that if a force is along the position vector from one point to another, specifically for this example that we've been talking about, it is a force from A to B, right? From A to B here. And then we can find the Cartesian format for force given the magnitude F and the coordinates, the start and end point, right? So we can express that. So we can express the force first as the magnitude times the unit vector along the line from A to B. And then the unit vector can be expressed as the position vector from A to B divided by its own length, right? And given that we know the coordinates, we can find out the Cartesian format of the position vector, and then divide this vector by its own length. So it is what we had at the end of the previous class. Okay, so uh, we are going to briefly talk about an example on how we can calculate, how we can evaluate the Cartesian format of a vector given given the magnitude of a vector and the coordinates of a start and end point. Okay, so given that we have a coordinate system here and we have a B point, which is a 1.75, 3, -5. Unit is in millimeter here. And A is 1, -4.5, and 10. Okay, so actually this cable or spring, it is along the line from B to A. Okay, and there's a force here pointing from B to A. It is stretching the cable here. the magnitude of the force equals to 100 Newton here. Okay, given those information, we are supposed to find Cartesian format of the force vector here. Okay, okay. So how can we approach that? Well, just to go back to the previous, page. Okay. So the answer is exactly as the last line, right? So we need to have the magnitude of force. It has already been in the problem statement, which is 100 Newton here, as well as the coordinate start point and end point can help us to define a position vector along the line of action. Do we know that? Yes. So we have the coordinates of B and A. And please note, for this time, the force is from where? From so the direction of force should be defined by a position vector from B to A, right? So B is the start point and A is the end point here. Okay, just plug in everything in the in the formula that we have in the previous page. It is here. Okay. So first magnitude, it is 100, right? Okay. Then direction. Direction is defined as okay. Direction is first defined as a position vector divided by its own length. First, the position vector should be at the numerator, right? And it is a vector, the components. So the coefficients of the components are using the coordinate of endpoint minus the coordinate start point. Specifically, for x component, the coordinate of endpoint is actually the actually the coordinate of a, right? A should be the endpoint here because the force is pointing towards a, right? Okay. So the x coordinate of endpoint, it is 1. So how about the x coordinate start point? It is a 1.75, right? Okay, minus 1.75. Okay, this is our I. And how about j? Okay, similarly, so it is a y coordinate endpoint 4.5 minus y coordinate point of start sorry, it is a y coordinate start point 3. Okay, j. And how about k component? Well, similarly. So it is a z coordinate of endpoint 10 minus z coordinate of start point 5. Sorry, it is a negative 5 here, so it will appear to be plus 5. Okay, 10 minus negative 5, it is 10 plus 5, k. Okay, those are our 3 components. Okay, so all we have as the numerator are what? It is actually a position vector from B to A. It is also a position vector along the direction of the force, right? Okay, please note that we need to multiply the magnitude with a unit vector along the direction of force. But now we only have we only have a position vector along the direction of force, and we need to convert this position vector of which the length does not necessarily equals to 1 to be a unit vector here such that the length equals to 1. Okay, and what we need to do is to divide the the vector on the numerator by its own length, right? And its length can be calculated as summation with squares of the components and then square root, right? Okay, summation of squares. all the components, then square root. Okay. So now we can go ahead and evaluate that. It will directly equals to negative 4.47 I negative 44.7 J, okay, plus 89.4 K. Please note that the unit here, it should be a force, so it is a Newton here. Okay, this is our answer here. Okay, okay, okay. For the purpose of practice, and I encourage to try to find out the magnitude of the force. Oh, sorry. So we've already have the magnitude of force here. So actually, it should be the direction cosine of the force here. Okay, but compared to what we've been talking about in the previous class, that is a Cartesian format, but in 3D. So here you see that you don't need to imagine the you don't need to imagine the angles, right? So now what we only what we only need to do is plug in every piece of information from the problem statement into the formula that we have here, right? So, compared to what we've been talking about in the previous class, so for here, it is so the implementation is even more straightforward here, right? Okay, so uh, what we've been talking about now, it is also will be used in the last problem in your homework. Okay, so there you will also have opportunity uh, to to practice it. Okay, so now it is actually the end of the I should say it is actually the end of the basic preparation for learning the major contents of our statics. Okay, so from now on, we are going to advance to a really new chapter here and to start to learn about force analysis. Okay, and for all we've been talking about in previous classes, it is trying to get us prepared and to know about what is the basic concepts that we have and the basic equation as well as the concept of vectors. How can we improve? How can we implement vector operation? Okay, okay. Let's open a new document here. So it's our lecture 9, particle equilibrium, but in 2D case. Okay, particle equilibrium, but in 2D case here. And does anybody remember what is a particle here? Okay, it is what we've been talking about at the very beginning of our semester, and we've been talking about the particle is actually a rigid body model of which the size can be ignored. And typically, we can represent a particle by a point, right? Okay, okay. So, and what is equilibrium here? Okay, so in the in the introduction part, we've been talking about actually the equilibrium is seen that's the velocity of the system or object that we're looking at is actually a constant, right? By seeing that it's a constant, it's seeing that's the direction and the magnitude, that is the speed of of velocity. It will it will not change here. Okay, so and as a consequence, so we can also derive with the Newton's first and second law, the most important equation, right? Uh, for our class, that is equation of equilibrium, right? Equation of equilibrium. That is equation of equilibrium. And we've been talking about it as the most important equation, right? And now you see that. Well, so it is seen that if an object is in equilibrium, then summation of all forces, actually I should say that it's all external force effects equals to what? Equals to zero. Excellent. Okay. Okay. So so if you look at here on the left-hand side, there's a summation of forces. It is the reason why we spend so long to try to practice how can we take summation of forces here, right? And now we've already get us prepared. We can go ahead to use this equation here. And please note that this equation is a vector equation. Okay, so if it is in 2D case, so this equation can be decomposed into two scalar equations. That is a summation of forces along x direction equals to zero. In other words, it is a thing that, okay, according to what we learned in the previous class, okay, summation of all forces along x direction is what? It's actually the x component of my resultant force, right? So in other words, it is saying that when a system is in equilibrium, then the x component of the resultant force equals zero, and y component also equals zero. Okay, so it is equivalent to what? The resultant force equals to zero, right? It is exactly what the original uh, the original vector summation uh implies here. Okay. Okay, so but for three-dimensional case, it will be similar. Uh, so the x component of the resultant force equals zero, y component of the resultant force equals zero, as well as z component equals to zero as well. Okay, okay, okay. So now I would like to see that by writing those equations, it is pretty straightforward here. But what really takes effort is to make use of those equations. And it is at where our students typically struggling with most. Okay, so now let's go ahead to practice how can we make use of this equation. It is also the reason why you are learning this statics. So the target is force analysis. And now started from here, we are going to talk about force analysis. Okay, given. Okay, A and B. Okay, we have a 10 kilogram object here. Okay, so now we have the 10 kilogram object is hanging here at point C, and well, C here actually it is connected with the rest cables AC and BC here. Well, uh, and give a little bit more about the geometric information. Okay, so the angle between AC and the horizontal direction is 45 degrees. And the slope of CB is expressed as this small triangle here. Okay. Okay. So given those information, we are supposed to find forces within cables. Okay, we are supposed to find forces within cables. Okay, so how can we approach that? Well, so although we kind of dealing with some probably summation of forces previously or summation of vectors for 2D case, but how can we apply it here? Okay, so before we apply that, we need to bridge the real problem, right? Right now, here's the real structure problem to force to a diagram that contains the forces here, right? Okay, so how can we convert a structure here to be a problem of force summations? Okay, so at least if you look at this problem here, so there's a no force vector here, right? Although we know that the object will be subjected to four forces and the cables they are subject to tensions, right? Okay, but we didn't see it. So now here's a one skill that very important is to expose the forces that we want to find out. That is to draw free body diagram. Okay, so it is a very it is a very start of force analysis. And please note, no matter how complex the problem is, it is always the first step is to draw free body diagram. Is to draw free body diagram here. Okay, so what is a free body diagram here? So a free body diagram is essentially you cut out one piece or one part of the system and you represent everything that used to connect it to the part by forces. Okay, I'm going to say it again. Free body diagram is essentially a diagram of a free body here. And a free body is what? Free body is that you cut out a part, a piece, a particle, a point of of the structure system, and then you represent all connections that used to exist that connected to the point by forces. Okay, it might be appears to be a little bit abstract here, and we're going to look into that. Okay, at least I believe you heard one keyword here is that we are going to cut out a part, right? We are going to cut out a part. So which part we are going to cut out here? Okay, so now it may not appears to be clear to you. So I'm going to first propose that we cut out point C here. Okay, we are going to cut out point C here. But why? Okay, why here? And at least how can we think about that? And here I can give you a hint. So if you look at a point C here, so the feature we see is that most cables are connected to C, right? Most cables are connected to C. And we also care about forces within cables. So it seems C is kind of important here. Well, but it may still not very clear here. Okay, so I'm going to first draw particle C here. Okay, so now we've already cut out C here. And as we've been talking about, by free body diagram, it is not only including the part that we cut out, we should also include in what? Okay, we should also replace everything used to connect it to C by forces. We should replace everything used to connect to C by forces. Okay, so what used to connect to C? First, if we look at the problem, we see that there used to have cable AC, right? Cable AC is used to connect it to C. Therefore, we should represent the forces within cable AC. Okay, so we should represent the cable AC by the tension forces that used in cable AC, right? Okay, so it should be a force along the line of AC, right? FAC here. Okay, okay, FAAC here. And please note, do we know the direction of the force AC here? Okay, so at least we know the force is along the cable AC, right? And since it is along the cable AC, therefore we know the line of action. Okay, we know the line of action is should be along the same direction of AC. So given that the AC, the angle between AC and the horizontal direction is 45 degrees, so we're gonna have this angle equals to 45 degrees here. Okay, okay. So how about, and in addition to FAC here, and what else do we have that used to connect to C? We have a cable CB, right? Similarly, we need to represent the effect of cable CB by what? By the tension force used to within cable CB, right? Okay, so we need to represent the cable CB by the corresponding forces. So here it is FCB. Okay, okay. So again, we know that the direction of cable, we know that the direction of the force CB, it is along the line CB here, right? So it can be given by this small triangle here. Okay, okay, great. And in addition to that, what else do we have? We have the object that is hanging on point C, right? So we need to represent what? We need to represent the gravity, right? We need to represent the gravity of the object as a force, right? So that is actually called gravity force here. And do we know the direction of the gravity force here? Typically, we know that, right? It is going downward, right? So we know that here for C, we also have a gravity force going downward. Okay. Do we know the magnitude of a gravity force here? Okay. So the problem tell us the object, so the mass of the object is 10, right? Okay. So we know the mass of the object. Can we find out the gravity, the magnitude of the gravity here? Of course, in the first class, we've been talking about the gravity equals to mass times gravitational acceleration, right? Okay, so now the mass is 10 kilogram, and the gravitational acceleration is how many here? And this piece of information is typically provided in your exam. Okay, so it is the same way provided as a quiz. So for international unit here, it is a 9.8 Newton per kilogram. Okay, so there's another way to express the unit here. It's a meter per square second. Okay, so you see that it is 98 Newton here. Okay, it is it is a it is a 98 Newton here. Okay, okay. So now have we already represented everything that you used to connect it to C by forces here? Seems yes, right? Okay, because previously we have cable AC, cable BC, and object all connected to C, and we respectively represented them by uh, by force AC, force CB, and the gravity here. And here, please note, we presumably assumed that the force in AC and force BC as tension. Why? Because if you look at the direction of AC and force AC and force BC here in the free body diagram, so they are going towards or away from my particle, away, right? It is away. And so since it is away, it is actually stretching. It is actually pulling my particle C, right? In other words, we assume that it is tension in our cables. Okay, so typically in our class, we are going to assume if we don't know exactly the direction of the force. And typically, what we know is that we know the line of action. Okay, at least we know along what is the direction of the line that the force is along with. But we typically sometimes are not clear about whether it is tension or compression. So typically, we are going to first assume that it is tension. Okay, some case it may be compression, especially we are going to learn about truss problems, and there will be compression. So if there's a compression, in that case, we're going to find that the magnitude of force is negative. Okay, in that case, we will know that it is a it is a compression here. Okay, so now we've already accomplished the first step, that is to draw the free body diagram of the problem here. Okay, so what is a free body diagram? Okay, now here is the case. Here is an example. Is that you cut out a part of the structure, and now here the parts that we cut out is particle C. And in addition to that, you replace every part that used to connect it to the part that you cut out by what? By corresponding forces. And now specifically here, you represented cable AC, cable BC, and the object respectively by force FAC, FCB, and the gravity. Okay. In other words, we can see that free body diagram contains the object that we're going to analyze and all forces on it. Free body diagram is a diagram contains the object that we're going to analyze and all forces on it. Okay? Okay. So, but another thing that I didn't explain, and I believe it probably kind of confused you, is that why we go with C. Okay. So why we pick up C here? Okay. So as we've been talking about, the free body diagram is a diagram of the part of the object that we're going to analyze and all forces on it. Of course. So, but we didn't talk about which object that we're going to analyze. So here's the case. We typically are interested in the object that can involve most of the unknowns of our interest or most forces of our interest. Okay, so if you look at the C here, it involves what? So C here involves force FAC, force. So actually it is a force in cable AC, force in cable CB, and the gravity, right? Okay. But if you look at what the problem is asking about, so the problem is exactly asking us the forces within cables. So now, if you look at the free body diagram we draw here, have it involved all forces within cables? Yes. Yes. So we go with C, we analyze C, we have already involved all forces of our interest, that is all forces in cables, in our free body diagram. That is the reason why we go with C. And for practice, you can try to analyze, for example, particle A or particle B here. And you're going to see that always it will make you confused, because if you go with a particle B here, it will only involve FCB. If you go with a particle if you go with particle A here, it will only involve FAC here. So the first problem is that So those particles is not effective enough because every time it will only include only part of the forces of our interest. And in addition to that, if you really try to draw the free body diagram B and A, it will, so when you cut that, you also cut the part. So you also cut, this is called the foundation of this. So typically in civil engineering, this part is called the foundation of the problem, and it is how it is connected to the environment, and it's so the force analysis for that is extremely complex. Okay, so now the reason why we pick up C here is why. Simply because it involves it involves the all the forces that of our interest, right? All the forces of our interest. Okay. In other words, it is the most effective. Okay, to summarize those, here's a one thing is that what is a free body diagram? In short, a free body diagram is a diagram contains the object that we're going to analyze and all forces on it. The object that we're going to analyze and all forces on it. And in addition to that, what part that we typically would select and to and to take it to draw the free body diagram, and typically it is a part can involve most of the forces of our interest, and for this case it is C. Okay, okay. So once we have the free body diagram here, we can go ahead to analyze it. Okay, so please note here it is a so it's one thing a little bit different from the previous classes is that so so previously we typically know the both the magnitude, the direction of all forces, but now if you look at the free body diagram, there's something that we don't know, right? We don't know the magnitude of FAC and FBC here, right? Okay, those are actually the unknowns that we have, but no worries. By seeing that we have the equation, we can first assume that we know those and assume those are and denote them respective to be FAC and FCP. Establish equations for those unknown forces, and then solve the solve the equation of equilibrium, and we can solve the unknown forces here. Okay. So now we can go ahead to go with step 2. Okay, what is a step 2 here? It is exactly to make use of the equation that we have. It's equation of equilibrium. Okay, it is equation of equilibrium here. We know equation of equilibrium is summation of forces. Okay, so for 2D case, the summation of forces along x direction equals 0, summation of forces along y direction equals 0. Okay, okay. So what we're gonna do is to do what? Okay, so now you already see that we've been seeing that the summation of forces along x and along y. That means we need to decompose, right? We need to decompose the forces that we have. Okay, by seeing that we decomposed, it is helpful if we include x-axis and y-axis. Okay, so typically x-axis is along the horizontal direction and y-axis is along the vertical direction here. Okay. So we can first decompose, for example, we can first decompose FAC here. FAC can be decomposed as we draw a line from the tip of the vector FAC to the horizontal axis, and then we have a right angle triangle where the head is the where the head is the vertical component FACY, and the base is a horizontal component, FACX. Okay. Okay. So similarly, we can decompose FCB as well. Draw a line that perpendicular to the x-axis, and then we have a right angle triangle now. Then the head of the right angled triangle, this is FCB Y, and this, the base, is FCB X. Okay. Okay, so now we graphically decomposed FAC and FCB here. And please note, we also have a gravity, but since gravity has already been along y direction, so we do not need to take to further decompose it. Okay. Okay. So now we are going to establish equations. So first, the summation of forces along x direction equals 0. And typically, if you look at the positive direction of x, okay, we assume the right hand, the direction towards the right to be positive. Therefore, we denote the positive direction to be the right direction here. Okay. And what do we have along x direction here? So by looking at the first diagram here, along x direction, we have the x component of FAC, that is FACX. We have FACX here, and we also have the x component of FCBX, x component of FCBX, right? We directly take the summation of those. For FACX, how can we find that out? Okay, so according to what we learned in the previous class, FACX equals to, first, we see that it actually belongs to a right angle triangle where we know we have the angle here that defines the direction of FAC, which is a 45 degrees here, right? 45 degrees here, and now do you think FACX is the opposite or adjacent? Okay, you may pause the video and think about that. FACX, it is adjacent, right? It is adjacent to the 45 degrees here. In other words, it is one of the sets that formed this 45 degree here, right? So adjacent equals to hypotenuse times cosine, right? Hypotenuse times cosine. And what is the hypotenuse here? The hypotenuse is exactly the magnitude of FAC, right? Exactly the magnitude of FAC, but we don't know the magnitude here. It is the unknown. We denote it to be FAC. Okay, the magnitude of FAC times cosine of 45 degrees. This is what? This is actually our FACX, but it is not complete. What have we already, or what in addition do we need to include here? And please don't forget the sign. Okay. So do you think the FACX is positive or negative here? Since it is going towards the left, but we assumed that the right direction is positive. So it is negative here. Okay, this is very important. Okay. Okay, so this is our FACX. And in addition to that, what else do we have? We have FCBX, right? For our FCBX, again, it is similar here. What? Okay, how can we find that out? At least we see FCBX, it belongs to a triangle here. It belongs to a triangle here, okay? And where the hypotenuse is FCB, okay? And the FCBX is the base here. And how can we find out the base here? Okay, so now I'm going to draw an angle here, and now I would like to appreciate the feedback from our students, so who actually suggested another way that we can go ahead to approach that and unify that with the case that we know an angle. Okay, so so I denote this angle here to be theta. Okay, so that is I denote the angle between FCB and FCBX to be theta here. So FCBX will equals to, since the theta is so the FCBX is the adjacent to theta here, right? And then the adjacent equals to hypotenuse times cosine, right? So the adjacent here equals to the hypotenuse times cosine theta here. But do we know the theta here? Okay, no. Actually, we don't know it. But what do we know? Okay, we have a small triangle here, right? Okay, so we have the small triangle here of which the base equals to 12 and the head equals to 5. And if you look at small triangle, since the small triangle and the big triangle, they are big fourth triangle here, they are similar, which means what is this small angle here? It is also theta as well, right? And from the small triangle, can we evaluate the cosine theta here? Okay, we can, right? By definition, cosine theta is what? Cosine theta is essentially the ratio between adjacent 12 to the hypotenuse. So cosine theta here, okay, so our cosine theta here is nothing more than the ratio between the base 12, and please note, now we are looking at the small triangle here. Base to hypotenuse, do we know the hypotenuse here? Since the small triangle is right triangle, then the hypotenuse equals to square root of the summation squares of the base and head, right? Okay, so summation square root of the summation squares of the base and head. Okay, so this ratio is actually the cosine theta here. And once we have a cosine theta here, we multiply the magnitude FCB by cosine theta here, we have FCBX, right? FCBX, it is the adjacent to theta here. Okay, again, positive or negative here. It is positive since it is going towards the right, right? Okay, plus. Is that okay? So is that all we have along x direction? Okay, please take one moment and look at your force diagram and make sure that you included all components. Okay, once you make sure that you know that is some summation of those components equals to 0. Why? Because it is in equilibrium, right? It is in equilibrium. Okay, okay. So now give me 1 second. Okay. So now similarly, we have summation of forces along y direction equals to 0. And please note, for y direction, we assume that it is upward. So it is upward is positive here. Okay. 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 So now we can go ahead to include all forces that we have along y direction. And what do we have along y direction here? By looking at the free body diagram, we have FACY, right? It is the y component of force AC. We have FCBY, which is a force vector, which is a y component of FCB. And what else here? Please don't forget we have the gravity, right? We have a gravity also along y here. Okay, let's include them one by one. First, FACY here. Okay, so now FACY, it is again, it is in the fourth triangle here, and it is a right angle triangle. And now, so the fourth ACY, it is the opposite or the adjacent to 45 degrees here. Please note, now it is the opposite, right? And opposite equals to what? Opposite equals to, okay, opposite equals to hypotenuse. Okay, I'm going to go bring it upward a bit. Okay, hypotenuse times it is opposite equals to actually the sine of 45 degrees here, right? Okay, it is sine 45 degrees here. Positive or negative? Okay, since FACY it is going upward, it is positive, right? Okay, this is actually our FACY plus. Okay, so Now, if you look at, so what we also need to include is FCBY, right? We also need to include FCBY here. Okay, so for FCBY, again, it belongs to the fourth triangle on the right hand part, right? And it is actually the head, right? Okay, and given that we denoted the angle theta here, okay, so now FCBY is the opposite or the adjacent to theta here. It is the opposite, right? It is opposite. Okay, so opposite, how can we find out that? It equals to hypotenuse FCB times now opposite, it is sine, right? It is a sine theta here. And do we know sine theta here? No. Again, it is similar to cosine theta here. We don't explicitly know that, but we can make use of the information of the small triangle and find that out. Okay, so we're going to replace the sine theta here. Okay, okay. So if we look at the small triangle, and now please note that since the small triangle and the big fourth triangle, they are similar, so we know that we have two angles here, they are equal, and the both of them equals to theta here, right? Okay, so if we look at the theta in the small triangle, what does sine theta equals to? By definition, sine theta is a ratio between its opposite to the hypotenuse. What is the opposite of the theta in the small triangle? It is a 5, right? It is a 5. Okay, what is the hypotenuse? Okay, so in the previous line, we have it, right? It is square root of summation of squares of the components, right? Okay. Oh, I'm sorry. So it is so we have not yet include all the information. Okay. So now we've already have FCBY positive or negative here. Okay, since it is going upward, it is a positive, right? What else do we have? Gravity, right? Gravity. Okay, so the gravity we've already have the magnitude which is which is a 98 Newton here. It is a Okay, it is a 98 Newton here. Positive or negative here. And please note, gravity is going downward. So it is negative. Okay. Okay. So now we've already have all the components along y direction, and we know the summation of those equals to 0. And to avoid distraction, I'm going to remove my denotation here. Okay, so to make the equation to be clearer here. Okay, so now we've already have two equations. Okay, now we've already have two equations. And how many unknowns do we have? Okay, FAC, FCB, right? We have two unknowns. Two unknowns, two equations. Can we solve that? We can, right? Okay, so by solving the two equations based on our knowledge in linear algebra, you can find okay, FAC equals to 97.9 Newton. And since it is positive, meaning what? Meaning that the direction of the force is exactly the same as what we assumed. It is tension or compression. We assume that it's tension. We find it is positive, meaning that it is tension. Okay, so typically in that case, we we see that is T here, T meaning that is tension. And we are also going to find out FCB equals to 75 Newton here. Again, it is positive, meaning that is tension. Okay, okay. So now if you look at the forces are tension, and you may think about that, does it align with your intuition? Should be, right? Should be here. It is aligned with our intuition. Okay, and again, so in addition, so cable typically cannot sustain compression. Okay, if you find that in cable you have a compression, either there's some problem with the problem statement or there's a problem with your problem solving. Okay, so this is one of our example uh for for equilibrium here. Okay, okay, okay. So now sometimes, okay, actually sometimes uh you are also required to analyze machine systems as well. For example, a for example, it's sometimes we will also be involved in analyzing police system here. So I'm going to introduce another example. Okay, that is a police system here. Okay, so actually the police system is composed of pulleys and cables, and sometimes it uh, can really help us to save the work and actually lower the magnitude of force that we need to apply. Okay, so pulleys and cables. Okay, so it is exactly one cable. So it is the reason why I can draw it by uh by one continuous line. And we have point A here, and we have point B here. Okay, and we have the C here. Okay, respectively to be the center of the polis. Okay, and the C is actually hanging on the ceiling, and A and B uh they have a cable. Sorry, each of them have a cable attached to them and connected to a object that with weight equals to 300 pound. Okay, and you are supposed to find tension in cable. Okay, you are supposed to find tension in cables. And please note, for this problem, all pulleys are frictionless, and weightless. Okay, all cables are frictionless and weightless here. Okay, okay. So I'm going to stop here for today's class, and you are encouraged to think about that and explore a little bit. And on Friday, we're going to continue from here. Okay. And please note if you have any question here, although probably in the upcoming few days, I probably cannot reply to you quickly, but when I see that, I will reply to you as soon as possible here. Okay. Okay.